Hello everyone, I'm here today to talk to you about another type of bond. They are called covalent bonds. And hopefully you remember and that you understood that ionic bonds were where something that had lost electrons and become positively charged was magnetically attracted to something that had gained electrons and become negatively charged. And those were just magnetic interactions. They weren't sharing any electrons. In a covalent bond, there is actual overlap of the atoms because they are sharing electrons to become stable. And so again, a covalent bond is one where atoms are sharing electrons to become stable, and there is an overlap between the atoms. This is determined whether they are going to share electrons or one will take another's based on their electronegativity, their attraction for electrons, where a greater electronegativity means the bond is more likely to become ionic, where one atom is stealing the electrons from the other. And the lower the difference in electronegativities between the two atoms in the bond, the more equally they will share the electrons. The quickest way to figure this out, especially if you don't have a chart with electronegativities of the elements, is that you could look to see if they are metals or not. If it's a metal paired with a non-metal, the difference in electronegativity will probably be greater than 2 and will probably be an ionic bond. If the difference between the two elements in the bond is less than 2.0, it typically means that they were two nonmetals in the bond. So a metal and a nonmetal is typically going to be ionic, and two nonmetals are typically going to share electrons and will be a covalent bond. So for example, when you look at the electronegativities for sodium and fluorine, you would find that the electronegativity for sodium is 0.93, and for fluorine it is 3.98. And so this difference is definitely greater than 2, and so when sodium and fluorine react, they will create an ionic bond. The fluorine has such a strong pull on electrons, it will pull the electrons away from the sodium completely with no sharing. If, on the other hand, it were hydrogen with fluorine, their electronegativities, hydrogen is 2.20, and so the difference between these is less than 2.0, and it would be a covalent bond. They would share the electrons, not evenly, since the fluorine still pulls the electrons more, but they would be sharing the electrons. And these are going to be representations of a neutral hydrogen atom and a neutral chlorine atom. The neutral hydrogen atom will have 1 electron, represented as 1 penny, and the neutral chlorine atom will have 17 pennies, representing the 17 electrons. So you can see the hydrogen has 1 electron in its first energy level. The chlorine has 2 in its first energy level to fill it. It has 8 in its second energy level to fill it, and it has 7 in its third energy level, so it is not completely full. For simplicity's sake, we're going to remove these from the full energy levels, and we're going to only have the outer or valence electrons represented, since they are the ones that react. We're going to remove all of the kernel or core electrons. So here, as well as in a dot diagram, only the valence electrons are represented. They're the only ones that react. And you can see that the hydrogen, its outer energy level is not full. It would be full with 2 electrons. The chlorine, its outer energy level is not full. It has 7, but it would be stable with 8. And so what happens is that these two bond, and they are going to share these 2 electrons with each other, and there will be overlap between the 2 atoms. And you would end up with a molecule of HCl, where these 6 electrons are only orbiting the chlorine. These 2 are spending their time orbiting the chlorine and the hydrogen. They would be represented on paper like this. These 2 dots represent the shared electrons, and they also can be represented with a line. And so when you're looking at diagrams that represent covalent bonds, a single line represents 2 shared electrons. Now, sometimes atoms cannot become stable by only sharing 2 electrons or 1 pair of electrons, and we'll look at those next, the multiple types of bonds. And we'll look at 3 examples. We'll look at an example of 2 chlorine atoms, 2 nitrogen atoms, and 2 oxygen atoms. And I'm only going to show the valence electrons, the outer electrons, because they're the ones that are going to take place in these reactions. Now these are 2 representations of neutral chlorine atoms. They have the 10 inner electrons removed, only the 7 valence electrons are showing, and you can see that neither one is stable. If they each share 1 electron with each other, they will be. And now you can see that this chlorine atom has 8 electrons orbiting it, and this chlorine atom has 8 valence electrons in that energy level to orbit it. This would be a single bond with 2 electrons. These are representing neutral oxygen atoms. They would have 2 electrons in their first energy level, but I've removed them for clarity, and they have 6 valence electrons each. Now if they were to share just 1 pair, each oxygen now has 7 electrons orbiting that energy level, and so they still are not stable. They can, however, share another pair. And that would look like this, where these 4 electrons are being shared between the 2 oxygen atoms. These 2 pairs and these 2 pairs are each stuck on that specific oxygen atom, but these 4 are shared. If sharing 2 electrons is a single bond, sharing 4 electrons is what is referred to as a double bond. And for the final example today, are 2 atoms of nitrogen. A neutral atom of nitrogen would have 7 electrons, 2 in the inner ring, which I've removed, and then 5 in the second energy level. And notice, if they share only 1 pair, now each nitrogen has 6 electrons orbiting around it. If they were to get a little bit closer and share 2 pairs, with these 4 being shared, each nitrogen has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And so it is still not stable, and they will share a 3rd pair. And now each nitrogen has the 6 that are shared and 2 on its own, for a total of 8 at that energy level to be stable. In our first example, with the two chlorine atoms that were separate, can be represented on paper like this, where they were separate, and then these are the electrons that are split between them, that are shared, that there are two of them, and it can be written as a dash, and that is called a single bond. Next, I'll show you how to draw and represent the double bond between the two oxygen atoms and the triple bond between the two nitrogen atoms. The last point I want you to understand about these covalent bonds, the types of things that you would find them in. If it's a number of atoms that are bonded together and it's neutral overall and they're connected with covalent bonds, that is what's called a molecule. If, however, there are a number of atoms that are bonded together, but somehow to become stable they needed to either gain an extra electron to form those bonds or lose an electron, those are called polyatomic ions, or an ion that is made of many atoms. And now the last point to make is to hopefully show you what diatomic, or have you understand what diatomic elements are now. Diatomic elements are non-metal elements where they exist in nature only as molecules that are formed of two atoms of that element. And there are only a few. And so when you read in a problem, or if someone says to you that it's referring to a molecule of oxygen, that needs to be understood to be O2, that a molecule of oxygen is one of the diatomic elements. They spell out this funny word, Hofbrinkel, when you put their element symbols next to each other. Similarly, if somebody says a molecule of bromine, it means Br2. A molecule of nitrogen is N2. A chlorine molecule is Cl2. So it's implied when you read a problem that if it says a molecule of hydrogen gas, that it's H2 for its formula, 2 atoms of hydrogen. Thanks for making it this far with me today. Hopefully everything was clear enough. You should be able to understand that atoms can share electrons to become stable, the ways to represent that on paper, and the different ways, single, double, or triple bonds, that they can share electrons to become stable.